Everyone. My name is Konstantinos Kagis, and today's presentation is about our project, Cyprus Quantum Communication Infrastructure, a co-funded project by the EU and also the Republic of Cyprus. So quantum key distribution, as you probably know or you heard these days, is a method of securely exchanging encryption keys using quantum properties transmitted via fiber. While this is in this quantum state, the nature of quantum mechanics ensures that any attempt to access the transmission will disturb the content. It does not prevent attacks, but basically ensures that an attempted attack is immediately visible and the key can be discarded, thus making the communication as safe as possible. Successful QKD paves the way for data to be transmitted using the latest and best symmetrical encryption. So current symmetrical algorithms which are considered can be safe against quantum decryption, which is a very, very important issue here. So what problems are we currently trying to solve? Well, the internet is filled with highly sensitive data and in general sophisticated encryption techniques which guarantee that such material cannot be intercepted and read. But with quantum computers, one could crack encryption in seconds, and this might be possible in the near future. So symmetric encryption like AES-256 is theorized to be quantum safe, but one can speculate that key sizes will increase in size to make it safer. So quantum cryptography is a method of encryption that uses the principles of quantum physics and in securing and transmitting data, and it basically creates security so strong that data coded in quantum state cannot be compromised without the sender being notified. So traditional cryptography uses technologies like SSL and TLS to secure data over the internet, but they have been vulnerable to this variety of attacks, as an attacker can change the communication between two parties, like users' browser and the web page or application, making them believe that they're still communicating with each other, whereas in fact they're actually being tricked. So with quantum cryptography, such an alteration of data is not possible, thereby strengthening the security of online transactions. Now, what do we gain with implementing this technology? What we actually want to gain the point-to-point secure communications between high-value sites and sensitive sites, such as governmental agencies, major banking and financial hubs, where data is way too sensitive and valuable. Application can be numerous and the potential market great for using QKD. Finally, applications that benefit to society are, as I said before, we want to provide secure communications and secure energy, financial sector, and provide a pan-European context of secure communications. So all these form part of secure communications backbone and ecosystem that we wish to secure in a democratic and society that we have in the EU. So the current public key cryptography protecting our sensitive data today will be rendered insecure, as I mentioned earlier, by the wide scale availability of powerful quantum computers. It is therefore critical that we keep our important confidential data quantum safe, and doing so requires a new approach to security. So current key generation that we can see on the left is mathematically generated, and key distribution effectively uses bright light. This gives us systems that the secret key, which is a pseudo-random key, can be predicted, and eavesdropper may steal this information and go unnoticed. And with the vulnerability to quantum computers, this gives us a system that the secret key may be in general vulnerable. So we need to make sure that we secure this technology, this network. So QKD is a method of communication that allows two parties to create a shared random key that is known only to them. Rather than mathematics, we're using quantum properties of light to generate secure random keys for encrypting and decrypting data, ensuring quantum key distribution protected transmissions, which can never be intercepted and decrypted by adversaries. This key can therefore be used to encrypt and decrypt messages, but more specifically, each photon has a random quantum state, and collectively the photons sent make up a stream of ones and zeros, just like basically with the bits in a binary system. So this key is truly random, cannot be predicted, and photons therefore cannot be cloned, making eavesdropping difficult by introducing errors. And therefore we have security of guarantee, security which is guaranteed by the quantum mechanics. So quantum key distribution is a cutting-edge technology that promises to revolutionize the world of data security. But however, there are many, as with any new technology, implementing QKD comes with its own set of challenges and opportunities at the same time when implementing it in real life. And with the transmission of single photon detector, current devices, which are readily available in the market right now, have limitations in distance as well as the types of protocols they are using or maybe using in the future. So we have the single photons which pose the distance limitation. We also have imperfections which may require extra implementation requirements, which means, of course, additional costs that we need to figure out, as well as we have noise, which is error and therefore cannot distinguish noisy channel from eavesdropping, and therefore we have to also solve issues with noise in channels. Now, a QKD protocol allows the distribution of symmetric random bit strings as a secure key that can be proven to be secure even against an eavesdropper with unbounded computational resources under some assumptions supporting the security proof model. So this kind of security is referred to as theoretic security. And since a QKD protocol is based on the laws of quantum mechanics, implementation security should be taken into account. Keys generated by QKD modules implementing the QKD protocol can be consumed by any cryptographic applications using symmetric keys, such as one-time paths, encryption, advanced encryption standards, hash-based message authentication code, etc. The basic element of QKD are a transmitter and a receiver, and each of which is referred to as a QKD module, as you can see here on the lower layer, the quantum layer. A QKD link connects the QKD modules, potentially with the help of a quantum relay point in the future, but at the moment the keys are shared via the QKD link. The QKD link is usually consisted of quantum channels. Well, it's consisted of quantum channel and a classical channel. The quantum channel is reserved for quantum signals, such as a single photon level coherent state of light, to transmit random bit strings. The classical channel, on the other hand, is reserved for synchronization and data exchange between the QKD modules, so it is also required. And the figure here, well, what we can see here is that we can see on the top layer, the quantum layer, we see the nodes that they communicate with each other using the classical communication channels, but the keys are distributed through the quantum layer. And we also have an additional layer, the key management layer, that supports the operation. So the application link where the encrypted data is transmitted can be any communication link in a conventional or future network. And therefore QKD is an add-on, can be considered as an add-on technology and service to existing future networks. So how all this started? Well, it started a while ago with the CYQCI initiative by the EU and of course the Digital Europe program that provided the funding across with the, the Republic of Cyprus for our case. where the EU aims to deploy advanced experimental quantum systems and networks combining quantum and classical security technologies. So what we aim here is to integrate these systems with existing communication networks and devise basically a testbed, develop a testbed that will allow us to test a number of use cases and contribute to the European technology autonomy in the highly strategic field of quantum communication technologies. So we want to use EU manufactured pilot devices and systems to support their deployment and work towards the maturity and compliance with the CYQCI security needs. Also, we want to test and function provision of QKD components and systems, their interoperability, and the end-to-end secure functioning of the system architectures, and also make the quantum networks available to industries in the future to operate the network's different layers, contributing to developing national-based production chains for supplying quantum communication components and systems. So CYQCI, it's also one of the EU-funded projects, as I said earlier, working towards the deployment of our first national QCI network. We consider it as a two-phase project, and currently we're in phase 1, where we try to deploy a national experimental QCI network across the island. And phase 2, hopefully in the future, will aims to upgrade the existing network into a cross-border type of network, enabling secure connectivity with the rest of the EU. So timeline is critical, but it's also dependable on the current state of the quantum technology across the EU and the maturity of the devices available in the near future. So the CYQCI consortium, as you can see here, the partners, we have the coordinator, which is the Cyprus University of Technology, and we have actively participating partners, which are Cyprus Telecommunication Authority, in charge of the deployment, of course, of the optical fibers, the network, and support, the technical support we have, and we will have throughout the trials. Then we have the Digital Security Authority, which is a governmental body, the Department of Electronic Communications, which is also a governmental body. And finally, we have the Cyprus Research and Academic Network, which is also a body that supports all universities across Cyprus and connects them together. So it's our academic network to support our academic and research activities. As mentioned before, this is a co-funded project by the European Union and the Republic of Cyprus. Now, the people here you can see are the main, this is our team from the Cyprus University of Technology, the core team. The project is coordinated by Professor Kyriakos Kalli, and I'm assisting as a co-coordinator. Dr. Mariella Minder is a technical coordinator, and Dr. Christiana Panagis is in charge of the space segment leader. Space segment, and we also had our latest additions, Dr. Andreas Ioannou and Dr. Stefanos Gerolachidis, who have recently joined our team. The objectives of our project are based and are in line with the COL's objectives, the Digital Europe program, which is basically to deploy an advanced experimental quantum network. This is going to be our test beds in Cyprus, but then it will sort of integrate with the rest of the EU test beds. We want to set the foundation for EU connectivity by participating through our optical ground station. I will come to that in a minute. And we also want to kickstart local research and innovation. That's why we try to engage universities, also activities, workshops that they will help this. Also support the EU technological autonomy by using EU manufactured equipment, and finally contribute to the international standardization efforts for quantum communications. Now, as you know, the project aims to deploy an advanced experimental quantum network, and the proposed architecture is based on a number of use cases that address the requirements of a variety of end user requirements, such as intragovernmental quantum security, cybersecurity crisis management centers, critical infrastructure protection, research and education, data storage and retrieval, and all these are basically in line again with the Digital Euro program call. So our use case partners are based on that. Another task that is not listed here that I ought to mention is to fulfill our cross-border communication obligation, which for Cyprus is a major challenge, given that the only way for us to connect with the rest of the EU is through QKD satellites and through space. So for that, the distance is limiting for us, given that we are far away from the. We have a limitation on the distance from Cyprus to the rest of the EU, so we need to use QKD satellites for the exchange of the keys. Our optical ground station will be based on Eagle 1 requirements effectively, and we hope that we'll be able to test it as soon as Eagle 1 is available. So, and with this, I have completed my presentation. Please remember to visit our website, which is CYQCI.eu, and also join our group on LinkedIn to get our updates and information about workshops, upcoming workshops and talks in Cyprus. Thank you very much for attending my presentation, and apologies for not being able to be present in Athens. Thank you very much.